Fatigue failure. Progressive, localized, permanent structural change occurring in material subjected to repeated or fluctuating strains at stresses having a maximum value less than the tensile strength of the material. This is the definition of fatigue failure. What is so interesting and puzzling about fatigue and the ultimate fracture it can cause is that the stress of repeated and fluctuating strains never exceeds the tensile strength of the material. In the initial stages, there are rarely any visible signs of fatigue, yet repetitive cycles of stress eventually form microscopic cracking. The cracks propagate. Eventually, fracture occurs. Fatigue fracture is a process occurring in 3 stages. 1, initiation. The repetitive stressing causes submicroscopic damage to the metal's crystal structure, leading to microcracks. 2, propagation. The microcracks grow deeper into the metal until the remaining uncracked section of the part becomes too weak to carry the load. 3, fracture. Sudden final rupture of the remaining cross-section of the part. Depending upon the metal involved, the environment, and the circumstances of stress, the final fracture may have ductile or brittle characteristics. Fatigue life. Predicting the fatigue life of a part or component is complicated. The part can be highly sensitive to small changes in loading conditions and local stresses. The local surface characteristics and the microstructural characteristics of the material also play an important part. Difficulties in predicting fatigue life arise from the inability to describe any one of various factors. When it is difficult to describe the local stresses and strains, when the loading history is not known, and the fatigue life characteristics of the material, its heat treatment, and prior processing are not known. To estimate the fatigue life of components or assemblies, the designer is also required to rely on experience with similar parts and must eventually depend upon qualification testing of prototypes or production parts. Laboratory fatigue tests on small specimens are not by themselves sufficient for establishing the fatigue life of a part. Yet laboratory tests are the major source of fatigue failure criteria. Tests can be used to isolate the loading variables involved in fatigue. Tests are useful in rating materials in terms of relative resistance to fatigue. Tests can also be used to establish the relative importance of factors affecting fatigue life, such as design, choice of material, fabrication method, surface finish, heat treatment, assembly technique, and environment. But on the whole, the best predictions of fatigue life can be obtained only when the results of laboratory tests are combined with the loading history and more accurate assessments of the stresses and strains in critical regions. In general, fatigue life can be expected to depend on many interrelated factors: the types of loading, uniaxial bending or torsional, the strength of material, the shape of the loading curve, frequency of load cycling, the loading pattern. Is it periodic loading at constant or variable amplitude, programmed loading or random loading, magnitude and direction of applied and residual stresses, the part size and shape, the fabrication method and the surface roughness, operating temperature, operating environment, other surface conditions such as decarburization, and of course, prior loading history. Traditionally, fatigue life is defined as the total number of load cycles required for a fatigue crack to initiate, then grow large enough to produce sudden catastrophic failure. The specimen separates into 2 pieces. Fatigue data can also be expressed in terms of crack growth rate. It is important to recognize that fatigue life and fatigue strength are not relatively fixed values for any given material. Fatigue life and fatigue strength are statistically variable values, subject to considerable scatter. Most laboratory fatigue testing is done either with uniform axial loading or bending. The amplitudes of the cyclic stresses and strains are imposed in either a constant or a random mode. The cyclic loads may also be fully reversed, applying equal tension and compression amplitude, or cycled relative to a tensile or compressive mean stress. The results of stress-controlled fatigue tests are usually plotted as graphs, showing the stress versus the number of cycles. The maximum stress, or stress amplitude, is plotted against the number of cycles to fracture, n. A logarithmic scale is used for the number of cycles. Stress is usually plotted on a linear scale. Each point on the graph represents the fatigue fracture of a separate test specimen. The resulting curve of data points is called the SN curve. A typical SN curve for AISI 2340 steel shows that the number of cycles the metal can endure before failure increases with decreasing stress. The two curves for AISI 2340 steel are typical for steel. The steel is subjected to constant amplitude cyclic stresses, appearing as a fairly straight sloping portion at the low cycle section of the SN curve, then straightening into a horizontal line at higher cycles. An SN curve usually represents the median life for a given stress. Median life is the life that half the specimens attain or surpass and half fail to attain. The fatigue lives of even supposedly identical parts may scatter over a very wide range. Since so many uncontrollable variables are involved, fatigue failure tends to be described in terms of probability. That is, fatigue failure is highly subject to statistical analysis. The horizontal portion of an SN curve represents the maximum constant amplitude stress that a relatively ductile ferrous metal can withstand for an infinitely large number of cycles with a 50% probability of failure. This is called the fatigue limit, or the endurance limit. In ferrous metals, this fatigue limit may disappear if a single overload cycle is imposed at some time during the testing. Also, most non-ferrous and relatively hard, brittle ferrous metals do not exhibit a fatigue limit. Instead, when the number of cycles is high, their SN curves continue to drop at a slow rate. Instead of reporting the fatigue limit for these metals, the fatigue strength is noted, or the stress to which the metal can be subjected for a specified number of cycles. Because no standard number of cycles exists, each table of fatigue strengths must specify the number of cycles for which the strengths are reported. Another factor complicating the prediction of fatigue life is the effect of stress concentration. Structural discontinuities that concentrate stresses in a material present a more complex problem, requiring both stress and strain concentrations to be determined. Structural discontinuities are sharp internal corners, notches, holes, or scratches, which act as stress razors. They cause local stresses to concentrate at certain points within the material. Local stresses at a notch may exceed the material's elastic limit, and this can result in local plastic deformation, even though the overall section stresses are elastic. Now, all this is fairly theoretical and complex, so before proceeding to the more down-to-earth study of fatigue, let's briefly review these factors that affect fatigue life and the methods used to predict it. Fatigue is defined as the progressive, localized, permanent structural change that occurs in a material subjected to repeated or fluctuating strains at stresses having maximum value less than the tensile strength of the material. Fatigue life can be defined as the total number of load cycles required for a fatigue crack to be initiated, then grow large enough to produce catastrophic failure. Fatigue life of a material is quite difficult to predict, owing to the large number of variables acting upon the metal, the inability to describe the local stresses and strains, the loading history, and the fatigue life history of the material. Most laboratory fatigue testing is done with axial loading or in bending. SN curves show the maximum stress and number of cycles required to fracture a specific material. The SNP curve is an SN curve representing the probability of failure. The slope of an SN curve does not level off at high cycles for most non-ferrous metals and some very hard ferrous metals, but gradually continues downward. Stages of fatigue fracture. The fracture surface that results from fatigue failure usually has a characteristic appearance. This characteristic appearance reveals the three progressive stages of fracture. The initiation stage is extremely difficult to see, even with the electron microscope. The submicroscopic alterations of the metal's crystal structure may exist within the patterns of the atoms that make up the crystal. But these irreversible changes do exist. They result from the repetitive shear stressing of the crystals at levels well below the tensile strength of the metal and even below the yield strength of the metal. This initiation stage of fatigue is difficult to envision and even difficult to describe. But these unseen, gradual, submicroscopic crystalline changes do exist and do tend to accumulate. Eventually, tiny cracks form at one or more locations, and the failure enters the second stage, propagation. From a practical standpoint, propagation is the most important stage in terms of identifying the type of failure. At this stage, the crack changes direction. The crack originates due to the shear stress direction in stage 1. But in stage 2, the crack changes to a direction perpendicular to the maximum tensile stress. This is the same as the direction of brittle fracture. The tip of the crack gradually progresses through the metal. The crack deepens and weakens the part as it goes. In relatively ductile metals, each stress application high enough to cause a crack to grow forms a tiny ridge-like striation at the tip of the crack. These striations are frequently visible in electron microscope examination of the more ductile metals. They are actually growth marks, analogous to growth rings in trees. These striations are characteristic of fatigue fracture in many metals. However, the striations are not always present, especially when the metal has little ductility. They are also easily damaged by corrosion, mechanical action, or post-fracture damage. Two sets of striations can be seen. The widely spaced striations are caused by a higher stress. The more closely spaced are caused by lower stress. The striations never cross. They are generally concentric or parallel to each other. Each striation marks the tip of the crack at some point in time during the test or service life of the part. The striations are very small, microscopic ridges and should not be confused with the much larger macroscopic ridges called beach marks, which may also be seen at very low magnifications. A very large number of microscopic striations may exist between each pair of macroscopic beach marks. The striations represent the repetitive cyclic strains on the part. The beach marks represent gross changes in the operation of the part. The final rupture stage is not really fatigue at all. Stage 3 is simply fracture, the last load application by which complete separation occurs. This final rupture may be either ductile or brittle, depending upon the properties of the metal. The importance of stage 3 in the analysis of fatigue fractures lies in the observation of the size, shape, and location of the final rupture. Size, shape, and location help identify the type of stress, its direction, the relative stress, and the strength of the metal in the part. This is a bending fatigue fracture of a large threaded shaft. The fracture began at a groove on the surface of the shaft. The beach marks indicate that the fracture proceeded almost entirely across the section before the final separation. Fatigue fracture characteristics. Macroscopic examination can reveal many characteristics of a fatigue failure. And of course, a macroscopic examination can be done at or near the failure site. A macro exam is particularly useful in correlating fracture surface characteristics with the size and shape of the part and with the loading conditions. The crack origin location may be found by first viewing the fracture surface at a low magnification between 1 and 100 diameters. The most common macroscopic feature characterizing many, but not all, fatigue fracture surfaces are the beach marks. Beach marks are centered around one or more sites corresponding to the fatigue fracture origin. When present, beach marks provide valuable information: the point of origin, the relative load intensity, and the crack dimensions at final failure. However, fatigue fractures will show beach marks only if one or more of the following factors were present: interruptions in service, large changes in loading magnitude or frequency, or oxidation or corrosion of the fracture surfaces during rest from intermittent service. Here, the beach marks in an aluminum alloy were produced by changes in the growth rate of the crack. These were the result of variations in applied load levels. The final fracture region covers about 40% of the fracture surface. A 4130 steel shaft failed in service. The fracture surface exhibits beach marks produced by oxidation of the fracture when the shaft was idle. The beach marks shown here were produced by a combination of variations in loading and the periods of rest normally experienced by an automotive crankshaft. In this case, the crankshaft is a ductile iron. Fracture originated at a notch in the root of a repair weld. The final fracture area was very small, indicating that low load levels prevailed. Under conditions of uninterrupted, constant amplitude loading, beach marks will not be evident. This fracture surface of a specimen tested in a laboratory shows the load was repeated at the same magnitude and without interruption until the final fracture. The fracture surface produced by the fatigue contains no beach marks. This condition is common in continuous laboratory fatigue testing or in continuous service. Examination of fatigue fractures by light microscopy is sometimes difficult. The features of the fracture surface may be high and exceed the depth of field of the microscope. Metallographic examinations of cross-sections through suspected fatigue fractures typically show a transgranular crack path. However, intergranular fatigue fractures can occur in hardened steels at low stress levels. A cross-section through a crack that has not grown enough to cause separation is often useful in showing deficiencies in design or manufacture, or the results of unanticipated service conditions. Electron microscope examination of undamaged fatigue fracture surfaces in materials up to about HRC 50 frequently shows finely spaced parallel ridges or striations. These fatigue striations are oriented perpendicular to the microscopic direction of crack propagation. With uniform loading, the spacing generally increases as the striations progress from the origin of fatigue. Each striation is the result of a single cycle of stress, but every stress cycle does not necessarily produce a striation. The spacing between striations depends strongly on the level of applied loading. The clarity of the striations depends on the ductility of the material. Striations are only visible in relatively ductile materials. Patches of fatigue striations in high-strength steel are less visible than in a wrought aluminum alloy or in low-strength steel. On the microscopic scale, the most important feature of the fatigue process is the nucleation of one or more cracks under the influence of reversed stresses that exceed the flow stress. Subsequently, fatigue cracks propagate by a series of opening and closing motions at the tip of the crack, producing the striations which form within the grains. The cracks initiate points of maximum local stress. These points are determined by the shape of the part or by surface and metallurgical imperfections, such as scratches, burrs, or other fabrication flaws. Foreign materials and hard particles in the metal can also determine the site of crack initiation. A great number of fatigue failures in otherwise lightly loaded structures originate in fretted or rubbed areas. In any jointed structure with some relative motion at an interface, fretting provides a possible location point for the initiation of failure. On the macroscopic scale, early crack extension occurs under conditions that give a typical smooth-textured, grained, flat-faced surface to the fracture. When produced under random repetitive loading or sequences of high and low stress amplitudes, the characteristic beach marks frequently result. It is possible for a fatigue crack to originate in the hard, strong region of a part and propagate into softer, weaker regions. This is usually due to heat treatment, imparting intentional variations to the properties of the material. Several different types of fractures may exist. In this induction-hardened axle, the fatigue origin was at the induction-hardened surface, heat-treated to about 46 HRC. The stress is concentrated in a fillet located at a change in the shaft diameter near a keyway runout. The fatigue crack gradually progressed around a large, roughly circular area. The shaft became so weakened by this large stress concentration that only one additional torsional load application was necessary to cause the final rupture. The well-defined chevron marks in the relatively hard, brittle, induction-hardened zone around the surface point toward the fatigue fracture origin. Inside the shaft, the considerably softer core shows a rough surface, characteristic of a rough tensile fracture in a ductile metal. This fracture is at a 45-degree angle to the shaft axis, typical of the fatigue and brittle fractures of shafts in torsion. When a crack has grown to the size at which it significantly reduces the load-carrying capacity of the part, a change in the direction of crack growth usually follows. In many parts, the fracture may, in general, still appear flat, but if the level of operating stress is low, the surface appearance becomes rougher and more fibrous. This indicates the change from crack extension to the final fast fracture. Notice there are no beach marks in the fatigue area. This is because the cycling in the test was continuous. As a general rule, low stress, high cycle fatigue produces flat face fractures. The fracture surface appears fine-grained and lightly polished near the crack nucleation site. This is where the stress intensification is least. As the crack grows and the intensity of stress increases, the surface becomes progressively rougher. In torsional fatigue caused by high stress, low cycle loading, the general direction of fracture is at 45 degrees to the axis of the part. The surface is fibrous and rough. The same rough fibrous appearance is found in certain areas of many fatigue fractures. The effects of variables. When analyzing fatigue failures, the effects of variables must be constantly kept in mind. Variables affecting a failure include overstress, stress concentrations, frequency of loading, mean stress, type of loading, and residual stress. The nucleation and growth of a fatigue crack are strongly affected by the shape of the part, the loading exerted, and the features on the fracture surface. Fracture analysis is relatively simple in a beam of uniform cross-section subjected to fluctuating or alternating stresses. The appearance of the fracture surfaces in test specimens is predictable. First, consider unidirectional bending. A beam of uniform cross-section subjected to pure, fluctuating, unidirectional bending has a bending moment that is uniform along the length of the beam. The tensile fiber stress at the surface is also uniform along the length of the beam. At high stress levels, fatigue cracks may initiate at several points along the beam on the tension surface before one of them becomes large enough to cause the final fracture. At low stress levels, only one origin is usually found. A related form of loading is cantilever loading. Here, the bending moment varies along the length of the beam. This means that the tensile fiber stress will also vary along the length of the beam. Fracture will initiate at the point of highest stress, usually adjacent to the rigid mounting, depending on the shape of the beam. Because of the shear stress component characteristic of cantilever loading, the direction of the maximum tensile stress makes a small angle with the axis of the beam. Consequently, a fatigue crack will usually propagate into that portion of the beam within the fixed mounting. Next, consider reversed bending. Reversed bending takes place when the loading on a beam is alternately minimum, maximum, minimum, with fully reversed tension compression surface stresses. With this type of loading, fatigue cracks may initiate on both sides of the beam. In pure reversed bending, the cracks on opposite sides of the beam may not be in the same plane. This causes the final fracture to be some angle other than 90 degrees to the beam axis. If the same load is applied to the beam in both directions, the two fatigue cracks should be symmetrical. The size of the final fracture zone indicates the relative loading of the beam. The fatigue cracks formed under fluctuating load and those formed under reversed load differ in one significant way. With a reversed load, each crack is opened in one half cycle, closed and pressed together during the other half cycle. This open and close action rubs and polishes the high points on opposite sides of the fatigue crack. Under unidirectional load, the rubbing is less pronounced or non-existent. Consequently, striations and beach marks are usually more observable after alternating unidirectional loading than after reverse loading. And then consider rotational bending. A rotating round shaft is commonly subjected to a bending load, often in addition to the torsion of rotation. A unique feature of this rotational bending is that during one revolution of the shaft, both tensile and compressive loading are exerted alternately at each point on the surface around the entire circumference of the shaft. This occurs in the region of maximum bending moment. Because the loading is axially symmetrical, a fatigue crack can be initiated at any point around the periphery of the shaft or at several points. Multiple cracks do not necessarily occur in the same plane. They are separated from each other by radial steps. These are called ratchet marks. Normally, the presence of multiple cracks indicates a relatively high applied load and rotational bending. Under low or moderate overloads, a rotating shaft may fail as a result of a single fatigue crack. When the shaft is always rotated in the same direction, the crack usually advances asymmetrically. That is, the direction of beach marks shifts in a direction opposite to the direction of shaft rotation. Asymmetric fatigue crack growth indicates bending and the direction of rotation. In this tractor power takeoff shaft, beach marks appear over a large portion of the surface. The fatigue fracture initiated in the sharp corner of a snap ring groove. Ratchet marks around the shaft periphery indicate a high stress concentration, but a low overstress. The original sharp points of the ratchet marks were damaged after the fracture by contact with the ratchet marks of the mating surface. No fatigue origins appeared on the upper left side of the shaft. Investigation revealed that the rotating bending force on the output spline was unbalanced. This caused maximum bending stress on the right side. Here, the fracture origins are evident. Consider torsional loading. Under torsional loading, the maximum local tensile stresses are at 45 degrees to the axis of the shaft. Under a fluctuating torsional load, fatigue cracks will develop perpendicular to the tensile stresses. Under alternating torsional loading, two sets of fatigue cracks, perpendicular to each other, may develop. Torsional fatigue cracks can initiate in longitudinal shear or in transverse shear. The relatively equal length of the cracks in each pair indicates that equal and opposite stresses have occurred during loading. At later stages of fatigue crack growth, one crack of a pair usually grows much faster than the other and eventually causes rupture of the shaft. In pure axial loading of a simple uniform beam, the stress is uniform across the cross-section of the beam. Therefore, a fatigue crack may, at least theoretically, initiate at a discontinuity within the member. However, it usually initiates at the surface. The magnitude of the nominal stress on a cyclically loaded component is often measured by the amount of overstress. Overstress is the amount by which the nominal stress exceeds the fatigue limit or the long life fatigue strength of the material used in the component. Under low overstress, the number of load cycles a component can endure is high. This is called high cycle fatigue. Increasing the magnitude of the nominal stress has the following effects. Fatigue fracture will occur sooner. Initiation of multiple cracks is more likely. The fracture texture is finer. The striation spacing is increased, and the region of final fast fracture is increased in size as the fatigue area is decreased. Very high overstress produces low cycle fatigue fractures. An arbitrary but commonly accepted dividing line between low stress high cycle and high stress low cycle fatigue is considered to be about 100,000 cycles. In practice, the distinction between low stress high cycle fracture and high stress low cycle is made by determining the dominant component of the strain imposed during cyclic loading. Low stress high cycle is elastic. High stress low cycle is plastic. Whether the dominant component is elastic or plastic in turn depends on the properties of the metal and the magnitude of the nominal stress. If the nominal stress is high and above the yield strength, gross plastic deformation will occur prior to fracture. However, true low stress high cycle fatigue will have stresses well below the yield strength. There can be no plastic deformation in the stage 2 fatigue zone. Fracture surfaces. The appearance of fatigue fracture surfaces will be affected by several factors. The severity of the stress concentration, the magnitude of nominal stress, and the type of loading. All sectional discontinuities and many common design features, such as notches, grooves, holes, threads, and keyways, increase the local stress level above the level estimated on the basis of minimum cross-sectional area. In addition to reducing the fatigue strength or fatigue life, increasing the severity of stress concentration has an effect on fatigue crack features. Initiation of multiple cracks is more likely. Beach marks usually become convex toward the points of crack origin. Under rotational bending loading, the beach marks may completely surround the final fracture zone, and combined stress states may be introduced, influencing the direction of crack growth. The appearance of fatigue fracture surfaces is based on certain principles. Number one, as local stress increases in the region of potential crack initiation, the number of active crack nuclei, or initiation sites, also increases. Therefore, at high overstress or in the presence of severe stress concentration, multiple crack origins will be seen. In most instances, the cracks from these origins will eventually unite to form a single crack front. Before the single crack front is formed, the individual microcracks will be separated by small vertical steps. These are the ratchet marks. At a stress just above the fatigue limit, the minimum stress for fracture, a single origin will occur. The entire fracture will emanate from this point. Principle number two. When no stress concentrations occur at the surface, cracks will propagate more rapidly near the center of a section. Propagation occurs because deformation constraints cause the stresses away from the surface to be triaxial and more severe. However, when a stress concentrating notch is at the surface, the stress near this notch may be more severe than when farther below the surface. Under conditions of severe notching, irregularly shaped crack fronts will sometimes be observed. 3. With an overload slightly more than adequate to cause a fatigue fracture, the region of final fast fracture will be relatively small. Under a much higher applied stress, this region will be relatively large. 4. In a fracture caused by rotational bending, the final fracture region will often be offset in a direction opposite to the rotation. 5. Fracture initiation usually occurs at or near the surface. This is because in most engineering situations, the surface is subjected to the greatest stress. For example, in bending or when stress concentrations are present. Subsurface origins have been observed in tension-tension or tension-compression fatigue, in Hertzian stress situations, such as the rolling contact fatigue of bearings, and in bending or torsion of case-hardened parts with no external geometrical stress concentrations. Crack initiation at the corners of drilled holes or at the ends of drilled holes may result from the presence of burrs remaining after machining. Since most cracks originate at the surface of a part, it stands to reason that placing the surface under compressive stress could be beneficial. And this is true. To increase the fatigue strength without increasing the weight of a part, many surface treatments are used to add compressive stresses. Nitriding, carburizing, shot peening, surface rolling, and overstressing, just to name a few. Work hardening and processing operations are used to increase residual stresses. Applied properly, these treatments put the surface in a state of residual compression. Applied improperly, these treatments can have a detrimental effect on fatigue life. In general, harmful residual stresses are introduced to parts and components in a variety of ways. They can be introduced during assembly by the misfit of structural parts and by a change in the specific volume of a metal accompanying phase changes, such as those occurring in quenching. Residual stresses can also be introduced by a change in shape following plastic deformation, and they can occur by thermal stresses resulting from rapid temperature changes. Stress concentrations affect the fatigue behavior of different materials differently. For instance, relatively brittle materials are more susceptible to the effects of stress raisers than ductile materials. And the flow and distribution of stresses change with section size or shape. In parts with a decreasing fillet radii, for instance, the stress increases at the point where the section size becomes thinner. In threaded components, a single notch introduces a considerably greater stress concentration effect than a continuous thread. The reason is that a continuous thread affords a more even distribution of the stresses on each of the sides created by the thread. That is, each thread is somewhat relieved of stress on both sides of the notch, all except the last thread on the bolt, which is relieved of stress on one side only. Thus, bolts frequently fracture through the first full thread. When a stress is predominantly torsional, the fatigue cracks usually start at the fillets of a keyway. The stress flow at the keyway is distorted by contact with the key, and the maximum torsional stress is concentrated just below the surface. Farther away from the keyway, the stress is smooth. The design of parts also has an effect on fatigue life. Mechanical and structural design encompasses two categories: configuration and material properties. Unfortunately, the materials are often selected for their machinability, their weldability, formability, resistance to corrosion or elevated temperatures, and not for their fatigue characteristics. But regardless of the controlling property, the material used in a part designed for fatigue resistance must possess an acceptable combination of many properties, and data may not be available for all specific materials, conditions, and forms. Summary: fatigue fracture. Stage 1, initiation. Stage 2, propagation. Stage 3, fracture. Fatigue fracture characteristics: striations, beach marks, final rupture, ductile or brittle. Variables affecting fatigue failure: overstress, stress concentrations, frequency of loading, type of loading, residual stress. Practices affecting fatigue life. With so much diversity in function, loads, stresses, materials, and environments, simple rules for fatigue-resistant design cannot be stated. However, a number of useful practices can be defined. When applied with good engineering judgment, these practices can reduce significantly the probability of fatigue failure. The available data are normally shown for a specific type of loading, specimen size, and surface roughness. Design guides that can minimize interference at the line of contact between mating parts are to provide generous fillets and radii, and to design parts with minimum mismatch at installation. This provides the lowest residual and preload tensile strains. The fatigue strength of good as-welded joints depends on the stress state in the load path through the weldment, the stress concentration at the toe of the weld, the condition of material in the heat-affected zone, and the presence or absence of inclusions and other imperfections in the weld. The fatigue strength of as-welded joints can be increased by cold working. The growth of cracks can be inhibited by introducing compressive residual stresses and redistributing fabrication stresses. Poor welding practices can create surface discontinuities, giving rise to stress risers where bending fatigue and torsional fatigue cracks can originate. Craters, undercutting, underbead cracks, and arc strikes are typical surface discontinuities from welding. Subsurface discontinuities, such as flux inclusions, incomplete fusion, and inadequate joint penetration, can originate cracking in parts loaded in tension, bending, and torsion. Under low cycle fatigue, the fatigue life of many metals is independent of grain size. In contrast, under high cycle fatigue, the fatigue life of many metals is increased when grain size is reduced. However, the effect of grain size on high cycle fatigue properties is difficult to assess, since many microstructures are altered by the same treatments that alter grain size. An improvement in resistance to high cycle fatigue brought about in some alloys by a decrease in grain size may be offset by a harmful effect on another property. For example, a decrease in grain size raises the smooth bar fatigue limit in some steels, but the small grain size may increase the notch sensitivity in these steels. The net result may be no improvement and no resistance to notch bar sensitivity. Discontinuities within a metal, either at the surface or subsurface, can adversely affect fatigue strength. These discontinuities may arise from primary or secondary working of the material or from melting practices. They may also be a characteristic of a particular alloy system. All wrought metal is shaped by thermal mechanical processing, generally by rolling, forging, pressing, or drawing. The movement of metal during these processes makes them susceptible to the formation of surface discontinuities. Laps, seams, and cold shuts can form. Oxides, slivers of the base material, or foreign material can be embedded into the surface. These surface imperfections produce notches of unknown severity that act as stress risers under load. They may also serve as sites for crack initiation during fabrication or in service. Burning results from heating a metal to a temperature so close to its melting point that permanent, irreversible damage is caused to the metal by intergranular oxidation or incipient melting. Burned steel usually contains both oxide films and voids or cracks at the boundaries of very large grains. These act as nuclei for fatigue cracking. Gross non-metallic inclusions at or near the surface are detrimental. They act as stress risers, forming points for the initiation of fatigue cracks. The larger the number of discontinuities, the greater the possibility of fatigue failure. Manufacturing operations that greatly affect fatigue strength include machining, grinding, heat treating, straightening, plating, welding, and identification marking. Components intended to withstand severe fatigue conditions should be finished with a fine cut or preferably ground. If possible, the direction of the final cut or grind should be near parallel to the direction of the principal tensile load. Quench cracks frequently cause failure in hardened steel parts. Quench cracks in steel originate from volume changes that occur in hardening. The transformation of austenite to martensite always expands with unfavorable conditions, and this may result in cracking. Many conditions promote the formation of quench cracks. Quenching media that are too severe, sharp edges and rough finishes, hardening temperatures that are too high, and hardening transformation that occurs last in the center of the part. Unless special precautions are taken when heating to high temperatures in an oxidizing atmosphere, the risk of losing carbon from the surface of steel is always present. Steels with severely decarburized surfaces show a marked reduction in fatigue strength. Sometimes components are unintentionally deformed. This can happen during manufacture, in shipping, or in service. Even though deformed plastically, these components can be straightened by any one of several cold or hot methods. But these initial deformations and subsequent working operations can introduce detrimental residual stresses, stress raisers, or cracks. Nicks, scratches, or locally work-hardened surfaces are all potential stress raisers. Plating is usually detrimental to the fatigue strength of plated parts. Carbon and low alloy steels, particularly steels of high hardness, are susceptible to hydrogen damage. The hydrogen is absorbed during the plating cycle and the associated acid cleaning cycles. Hard plating materials, such as chromium, are usually in a state of residual tensile stress after being deposited on the base metal. Cracks develop in the plating material. The cracks act as stress raisers, and if the cyclic stress amplitude is sufficient, the stress raisers may produce cracking in the base metal. Identification marking on components can introduce excessive stresses. The location and method of marking this information is particularly important. Marks should not be in areas of high tensile, bending, or torsional stresses. For castings and forgings, raised letters introduced in the dies or molds are preferred to indented stamps. For marks on machined surfaces, a marking ink is preferable to using an electric etching pencil or vibrating mechanical engraver. A cold steel stamp is probably the most abusive to the steel. However, using steel stamps in a non-stressed area may be preferable to some other type of identification mark in more highly stressed regions. Characters with straight lines tend to cause the most cracks, although characters with rounded corners also cause cracking. If steel stamps must be used, they should be low-stress stamps or dull stamps that will cause the least trouble, particularly if light impressions are made. The stamping should also be located in areas known to be low stress. Thermal fatigue is a residual stress effect. It is caused by simultaneous mechanical restraint and repetitive thermal changes. The thermal expansion is caused by a local temperature increase. The expansion acts against a restraint, usually the harder, stronger, cooler metal adjacent to the heated metal. When hot, compressive yielding may result, and during cooling, the compressive yielding, in turn, causes tensile residual stresses from the thermal contraction. Repetitive thermal cycling can result in fatigue crack formation and propagation each time the metal cools to the lower temperature. The restraint to the thermal expansion may be external, mounts for pipes, exhaust manifolds, or other rigid structures, or it may be internal, as the cold, strong metal on the inside of a part still unheated by the heat on the outside. Brake shoes heated by friction, clutch plates, and many engine parts are subject to uneven heating. Low-cycle thermal fatigue failures can be identified by multiple initiation sites that join randomly by edge sliding to form the main crack, transverse fractures, an oxide wedge filling the crack, and transgranular fracture. True thermal fatigue occurs in such components as internal combustion engines, where thick-section cast materials are used. Thermal fatigue also occurs in appliances and heat exchangers, where thin wrought material is used. When cast materials are used, the desirable design features are uniform sections, mild strain gradients, and short flake graphite microstructure. In oil-fired and gas-fired furnace heat exchangers, the thermal cycle is very important. The thermal cycle controls temperature gradients. In thin sections, external constraints are of minor importance. Under certain circumstances, thermal fatigue and stress rupture failures blend into each other. Thermal fatigue is the basic mechanism in failures caused by numerous short heating and cooling cycles. Stress rupture becomes important as the cycle times increase. Stress rupture, therefore, is primarily a long-term rate process. Most thermal fatigue fractures are low cycle, high strain. The fracture surfaces are rough and faceted at or near the initiation sites. They are more fibrous with shear lips at 45-degree angles in the final fracture area. Thermal fatigue frequently can be prevented by reducing steep thermal gradients. This is brought about by better cooling, less aggressive friction materials, and the use of materials with higher thermal conductivity. The other factor, restraint, can frequently be minimized by designing flexibility into the system. The use of expansion joints and loops, curved sections, bellows, and sliding joints permit the hot sections to float or expand and contract unrestrained. Thus, compressive yielding cannot occur when the metal is hot. In most instances, corrosive environments reduce the fatigue strength or fatigue life of a given material. The effect varies widely, depending primarily on the characteristics of the material-environment combination. The environment affects crack growth rate, the probability of fatigue crack initiation, or both. For many materials, the stress range required to cause fatigue failure in an aggressive environment diminishes progressively with time and with number of cycles compared to an inert environment. This is seen as a progressively wider separation between fatigue curves for inert and aggressive environments. Corrosion fatigue tests on smooth specimens of high-strength steel indicate that very large reductions in fatigue strength or fatigue life can occur in salt water. For instance, the fatigue strength at 10 million cycles could be reduced to as little as 10% of the fatigue strength in dry air. In these tests, the main role of the environment was corrosive attack of the polished surface, creating local stress razors that initiated fatigue cracks. Salt water also increases the crack growth rate in steels, provided the cyclic rate is 6 cycles per second or slower. Surface features of corrosion fatigue crack origins vary with the alloy and with the specific environmental conditions. In carbon steels, for instance, cracks often originate at hemispherical corrosion pits. Often these contain significant amounts of corrosion products. The cracks are predominantly transgranular and may exhibit a slight amount of branching. Except where they intersect the free surface, they resemble fatigue cracks that are not environmentally induced. Surface pitting is not a prerequisite for corrosion fatigue cracking of carbon steels. Corrosion fatigue cracks sometimes occur in the absence of pits. Extensive corrosion often damages fracture surfaces and can make positive identification of the fracture mechanism difficult. The environment may also alter the mode of crack propagation. In hydrogen, for example, fatigue crack growth by quasi-cleavage has been observed. This is considerably different from the typical mode of fatigue crack propagation. Summary: practices affecting fatigue life. Part design: as welded joints, primary and secondary working, burning, gross non-metallic inclusions, manufacturing operations, quenching, decarburization, plating, and identification marking. Thermal fatigue is a residual stress effect. Principal cause: repetitive thermal change with simultaneous mechanical restraint. And finally, environment will affect crack growth rate and the probability of fatigue crack initiation. It should now be quite apparent that the fatigue life of any part or assembly is dependent upon so many factors and variables that measurement and prediction is difficult at best. And with so many unknown factors playing parts in the process, fatigue life is essentially a function of probability based upon the function and comparison of supposedly identical parts and assemblies. The variables affecting fatigue life are always present and responsible for the scatter of fatigue life usually observed. And it is with this in mind that extensive component fatigue testing is continually practiced throughout the industry.